Hello everyone, hope you guys are doing really good. Today we're going to start the discussion on dynamics of robotic manipulators. And this is going to be part one of the discussion. In that, we're going to start with introductory examples, and then we're going to construct the Lagrangian, which accounts for two expressions in it, one corresponding to kinetic energy, the other which corresponds to potential energy for n-link robots. So we're going to use these concepts later on in other parts to construct the equations of motion for dynamic response of robotic manipulators. So let's start the discussion. Consider this robotic manipulator moving. And for that movement, if we're only interested in finding out the position, orientation, velocities, and acceleration of the joints and end effector, then we will be considering only kinematics. But if on the other side, in addition to that, we are interested in finding out the forces and torques associated with all these joints and end effector, then we will be interested in dynamics as well. And it is going to be important also for better designing the robots to consider the inertial factors and all the other derived factors we will see later on. So in this particular case, you have to realize that kinematics is going to consider movement, but it will not consider the forces and torques associated with it. Whereas in dynamics, you have to add kinematics alongside those inertial aspects as well as forces and torques. So for that reason, this study is important. So that's why we are doing it. Essentially in dynamics, we're going to formulate equations of motion. In these equations, we're going to incorporate all those kinematics that we have already formulated, in addition to other factors like gravitational, inertial, and other derived factors. But the question over here is that what is going to be the approach taken to define or derive those equations? There can be multiple ways, obviously, but the most popular ones are what we call Lagrange's approach, and the other one what we call Newton's approach. Now you have seen Newton's approach so many times, so I'll try to start from here, but essentially we will try to keep the focus on the Lagrange's approach. So this is what we intend to do, because this is going to make our life a bit easy, and also for the sake of designing better controllers, we will love to have Lagrange's approach incorporated. So we will start from a Newton's approach, and we will try to kind of find how Lagrange's approach is equivalent to that, and then we're going to stick to Lagrange's approach. So we're going to proceed along those lines. We will start with a very simple exercise to consider a one-dimensional system. And in that, you can consider that there is a mass m which is being suspended in air. So obviously this mass m is going to try to hit the ground, but it is being pulled up as well. So you can consider that there is an electromagnet which is trying to pull this thing up. So it is kind of a magnetic levitation that we are trying to experiment over here. So if we have to find out the equation of motion for this, we can try Newton's approach first. And if we try to do that, there is a simple straightforward method. The very first step is going to be to define the coordinate axis or coordinate frame. So in this particular case, you can say that with the center of this mass, I can say that this is the y-axis, the positive sense of y. So in this case, you have defined the y-axis. So that is going to be step number one. Step number two generally is to draw the free body diagram. And you can very simply draw that. And obviously I can do that over here, that the mass is being pulled down. So that is going to be the weight, which is mg, and it is being pulled up as well. So that is going to be the external applied force being executed by the electromagnet. So this is the free body diagram. So that would be step number 2. Step number 3 is to use the Newton's approach or the formula, which in this particular case would be a very simple straightforward formula which says that the summation of forces along the selected coordinate frame, which is y-axis, to be equal to mass times the acceleration along y direction. So in that case, you can simply use the free body diagram and you can sum everything up. So f of t is along positive y minus mg is going to be equal to mass times the acceleration along y direction, which is y double dot. And then you can obviously rearrange that like my double dot plus mg on one side and the applied force on the other side. So that is going to be your equation of motion. And essentially it is a second order differential equation which incorporates the inertial and the gravitational aspects as well as the applied forces. So I'll raise this question over here, that can we find out the same equation of motion using Lagrange's approach? Yes, we can do that, but for that we have to write down the expression. The equation of motion generally in Lagrange's approach is constructed when you take the time derivative of partial derivative of Lagrangian with respect to generalized velocities minus partial derivative of Lagrangian with respect to generalized coordinates or displacements to be equal to generalized forces or torques. So this is the generic expression. I'll label this as expression A. So obviously you can see that we require Lagrangian formulation, and that is not complex. It is just like the kinetic energy minus the potential energy. The kinetic energy for the suspended mass is quite simple. This is going to be half my dot squared, whereas the potential energy is also very simple. This is mass times the gravitational acceleration times the displacement, which is y in this case. So you can obviously see that Lagrangian for that matter is just like this expression, my dot squared minus mgy. Now I'm going to use this to construct the partial derivative of this Lagrangian with respect to the generalized velocities, which is in our case y dot. So this is going to be equal to this expression, and in this expression you can readily see that there is only one term which involves y dot. So that is going to give us a very simple output that is equal to my dot. Now once you have defined that, you can take the time derivative of partial of L by partial of y dot, and that is going to be equal to d by dt of my dot, and that is quite simply my double dot. Now take this as expression number 1. Now you can take the partial derivative of Lagrangian with respect to the generalized coordinate, which is y in our case. So that is going to be partial by partial of y of half my dot squared minus mgy. So there is only one term which involves y in it, that is minus mgy. So that is when taken the partial derivative of with respect to y, this is going to be simply minus mg. So this is going to be your equation number 2. So using these two equations, equation 1 and 2, and plugging in equation A, so that would mean that equation A can be rewritten like you have my double dot minus plus mg to be equal to the generalized torques, which in this case the applied force, which is perfectly aligned with the generalized coordinate. So that's why it is going to be simply f of t. And this is the equation that you have derived already using the Newton's approach. And you can see that happening right over here. So at this particular stage, we can convince ourselves that we're going to reach to the same conclusion. We will have the same system, but for multi-body systems, we're going to observe that structurally, the Lagrange's approach is going to give you coupled second-order nonlinear differential equations, which are going to make our life a bit easy when we are going to try to find the better controllers for that. So we will see that later on, but at this particular stage, we can have this realization that the same system, when modeled using Newton's approach, is going to give you the same result as in Lagrange's approach. So for that reason, we will stick to Lagrange's approach in the subsequent discussions, and we will see how the robotic systems can be modeled. Let's now have another example and add a little bit of complexity in it. So in this case, we are going to consider a single link manipulator. Now you're going to assume that you have a motor available with you, and this motor is going to have a shaft rotation associated with it. So that shaft rotation is labeled as theta m, for example. Now this motor is connected with a gearbox. So let's add that over here. So this is the gearbox available, which is going to obviously reduce the speed and increase the torque. And that is going to be connected with a link. Because it is a single link, I can assume that this is going to take somewhat of this shape. To be drawn simply, I can have this kind of shape for that link. Now this link obviously is going to have a center of mass, which I'm assuming because of the simplicity of the link is going to be centered somewhere over here, where you have the mass of the link concentrated. So let it be like that. But the interesting thing is that because you have a gearbox attached with the motor, it is going to reduce the speed and obviously increase the torque. So that is going to have another angular displacement over here. Let it be theta L, and obviously the torque is also going to be associated with that, corresponding to the link which is rotating. Let it be tau L. Now this is how we're going to set up the arrangement of a single link manipulator. But since we have to use the Euler-Lagrange approach, we have to follow certain steps which are consistent with this method. So the very first step would be to find out the generalized coordinates. Now in this particular case, you have a single degree of freedom system. Obviously there is a shaft rotation which is moving the link with that. But since we have identified theta m and theta L to be two different thetas, so we have to see that what connects the two. And obviously because you have a gearbox in the middle, which is going to have a gear ratio, so that is the gear ratio which connects the two. So that would be something like you have theta m to be equal to the gear ratio times the theta L, which means because you have R ratio 1 as the gear ratio. Now that would mean that you can now identify a specific generalized coordinate on the basis of that. So in that case, because we are interested in how the link moves, so that's why I'm going to choose the generalized coordinate to be theta L. Now this is the first step. Let's move on to the second step. That would be to find out the kinetic energy. Kinetic energy expression is K, which is going to be equal to, in this particular case, uh, on the basis of moving bodies in the system. And you can see that since the motor is going to have a rotation, so that's why there is going to be a moment of inertia associated with that, as well as the link is moving, so that is going to have that uh, component as well. So if I write that one down, this would be something like half the moment of inertia of the motor times the angular velocity of the motor, theta m dot squared, added with how the link is moving, which is going to have its own moment of inertia, let it be like JL, and theta L dot squared. Now, since you have defined theta m to be r times theta L, so you can now plug in that value. So this is going to give us half r squared Jm plus JL, and then you can have theta L dot squared. So this is how we have manipulated, because the selected generalized coordinate is theta L. So the velocity corresponding to that is what would be more important for us. So in this particular case, you can say that this expression over here can be labeled as the overall moment of inertia. Let it be like J. So once you have got the kinetic energy expression identified, in the context of the generalized coordinates and the generalized velocities, you can move on and find out the expression for the potential energy. So that would be step number 3. In this case, obviously you are going to see that how the link is having its own displacement identified, and that would be correlated with the potential energy expression. So I'll make one little diagram over here. That would be something like, if you have a link which is rotating, probably if I view this whole scenario from this view, you are going to consider possibly this as the pivot point, and the link is going to have somewhat this angle made with the vertical arrangement. So let it be like theta L defined uh, to be consistent with how we define the pendulums. And in that, if the center of mass is structured over here, which goes down like this, mg over here, I need to identify what is going to be the length from the pivot point all the way to that center of mass, and let it be L. Now, if you define that, you can say that this point where the mass is centered, it is going to move in this fashion, and I'm going to be interested in finding out what is this height from this point all the way to the lowest point over here. So this is what I'm interested in. So that is going to be when you define mg, and let me use red color over here, h over here. So that is needed to be identified. So I can readily see that you are going to have this dimension from here all the way to this to be equal to L cos of theta L. And for that reason, the height is going to be quite simply the total length minus L cos of theta L. So I'm going to write that one down over here. So this is mg times and I'm going to use a red color for that, L minus L cos of theta L. So with this realization that you can take the L common from there, so this is going to be mgl, and then you have 1 minus cos of theta L over here. So this is the potential energy expression that we have figured out. Now, on top of that, I'm interested in finding out, using these two expressions, to find the Lagrangian. And this is quite simply L, which is kinetic energy minus the potential energy, and that these two expressions are already there, so you can use those to find the Lagrangian. So this Lagrangian can be written once again like this, that you have half this moment of inertia times theta L dot squared minus potential energy expression, which is already written down, mgl. You have minus cos of theta L. Now you can move on to the step number 5, and that would be to find out partial of this Lagrangian with respect to the generalized velocities. So that would be equal to, actually in this case, partial of L by partial of theta L dot. And that you can do very easily. This whole expression that I've written down over here. And when you do that, this is going to be very simply, because there is only one term which involves theta L dot, so that is going to be r squared jm plus jl, which I can write as j as well. Then you have theta L dot. So that is equal to partial of L by partial of theta L dot. So that is available. Then you can use this to construct step number 6, which is going to be d by dt of this expression that you have derived already. So this is going to be equal to, for that reason, this whole expression, and you have theta L double dot, because that's the only time dependent variable in the expression. Moving on, you can move to step number 7, which is going to be partial of L by partial of theta L now, which is the generalized coordinate in our case. So that is going to be very simply structured once again using the expression of Lagrangian that we have already listed. So that's going to be, just for the sake of completion, I'll write that one down quickly. And you can readily see that the very first term is dependent on theta L dot, so that would not be important for us. So that is not going to be included in the final expression. But this term corresponding to the potential energy is going to have its role to play. So that is going to be, for that reason, important. So when you do that, that is going to be actually partial of theta L of mgl cos of theta L, because this term as well as this term is not going to be needed because it is not dependent on theta L. So that is going to give you the final expression for partial of L by partial of theta L, which is equal to minus mgl sine of theta L. So this is step number 7. And now what you can do, you can recall the expression which is obviously the step number 8, and that is when you take the time derivative of partial of L by partial of, in this case, theta L dot minus partial of Lagrangian by partial of theta L to be equal to the applied torque, which is the generalized torque over here. So now you can see that this expression is already available in step number 6, and this is already available in step number 7. So now you can use that. So this would mean that r squared gm plus gl theta times theta L double dot minus minus plus mgl sine of theta L is equal to the generalized force or torques, which in this case is simply because the motor is the link is rotating and motor is applying the torque after the gearbox right on the link, so that is going to be tau L. So this is the equation of motion. Now, if you observe what is happening in this equation of motion, there is a little aspect that we need to further investigate, and that is this tau L, which is the torque available at the link. I think we would be more interested in finding out what is happening with the motor, because we are going to design a control system for that, and for that reason we will have the motor torque to be controlled so that it behaves in a desired form. So for that reason we would love to have how this motor torque is translated all the way to the link torque. So the relationship between U and tau L is needed to be structured. So that's why I'll say that actually what happens is that you have motor, and then you move on to the gearbox, and then it moves all the way or transfers all the way to the link. So in that particular case, actually the process is that the link torque is going to be equal to the motor torque which is available minus the damping available in this whole arrangement, and this damping is going to come partially from the gearbox as well as from within the motor where you have bearing surfaces available. So that is actually in true sense equal to R times the damping available at motor plus damping available up till the link. So this damping multiplied with theta L dot is going to be the component taken away from the motor torque. So that is the expression that we have to kind of plug in over here. So when you do that, that is going to be something like this, that you have R squared Jm plus Jl, which is the total moment of inertia times theta L double dot, and then you can have this minus b theta L dot taken on this side, so this is going to change the sign, b theta L dot is going to be placed over here, plus then you have mgl sine of theta L. So this is going to be equal to the motor torque. And now this is the equation that we can use to have insight of how the motor is behaving, or how that input provided by the motor is translated all the way, incorporating all the components in the middle. So this is going to be the updated equation of motion. Both are valid equations of motion, but you have to consider that when you are going to have a motor attached, that motor is needed to be controlled in a specific fashion. So you would be more interested in finding out how this motor torque is translated into the dynamics of the system. Now we can see that if we exhaust this expression, this is going to give you the Euler-Lagrange equations for your systems. And since you're going to have n generalized coordinates, so you're going to find out n coupled second order nonlinear differential equations, which will define the dynamics of the system. Now, in case of robotic manipulators, you have to make a little observation over here for the generalized coordinates. Now, these generalized coordinates are going to be according to the n Dennevert-Hartenberg joint variables that you have already identified. So you can recall that we said that we are going to have thetas as the variable for the revolute joints and d's as variable for the prismatic joints. So you're going to use the same variables that you have already identified in case of Dennevert-Hartenberg convention. So that's why you have to be consistent over here. But this is going to make the identification of generalized coordinates much more easy in case of robotic manipulators as well, which in general other mechanical or electromechanical systems, it becomes a bit cumbersome sometimes. So this is a good thing that we have already defined the Dennevert-Hartenberg frames, so we can probably use the same variables defined over there. So this equation is going to be formulating you the n-coupled second-order nonlinear differential equations defining the behavior of robotic arms. So up to this point, we have only considered very simple systems. Initially, we discussed the 1 DOF suspended mass, and then we discussed a single-link manipulator. But in most of these practical applications, you are going to find n-link manipulators doing their job. So we have to find out some general case where you can discuss such systems. So for that reason, I would say that it would be better that we can start from finding the expression for kinetic energy and then find out the expression for potential energy, but both in general cases, which incorporates the n-link possibility, so that we can use these expressions for any type of robots, whether it is 6 degrees of freedom robot or 3-link manipulator, or even more complex collaborative robots where you have a degree of redundancy added in the system. So all these possibilities are needed to be exhausted, so we are interested in finding out a general case scenario. So this is going to be the quest in this subsequent discussion. Before we get into the general expression for kinetic energy, I must ask you to recall that for a concentrated mass m, which was being pulled down because of the gravitational pull, and pulled up as well because of the external applied force, we started from identifying a generalized coordinate for that, and that was the y-axis. Now in this continuation, we said that the kinetic energy for this body is going to be equal to half m y dot squared, where y dot is the velocity along the generalized coordinate. Now in this particular scenario, the things are quite simple, but you may have a body which is a bit of irregularly shaped. It may be something like this. And this body is going to have some frame which is going to be attached with the body. Possibly we may define it to be like this. And another frame which is going to be the inertial frame, possibly somewhere displaced like this. So this is the fixed frame, and this is the body attached frame. And if this body having a mass m is moving and moving in 3D space, it is going to have the linear velocity component to be having 3 components in it, like x dot, y dot, and z dot. And it is going to have an angular velocity vector as well, which is going to have 3 components as well, omega x, omega y, and omega z. And these are going to be with respect to fixed inertial frame. Now, it would mean that obviously there is going to be a somewhat refined expression for kinetic energy, obviously. And that is going to have 2 components in them. One portion which is going to be corresponding to the translational part of the kinetic energy, and the other one which corresponds to the rotational part. So the translational part is going to be half m, this linear velocity vector transposed multiplied with the vector itself, which is going to be squaring the velocities. And then you have the rotational part, which is going to be half omega transposed times the inertia tensor times omega. So this is going to be somewhat upgraded version of the kinetic energy that we have seen earlier. So one needs to make this shift from a one-dimensional to three-dimensional movement, and for that one needs to upgrade. Now with this realization that you are going to define a vector from the fixed frame all the way to the body attached frame, and that vector is going to be defining how the linear velocities and angular velocities are structured, and also for the inertia tensor as well. So we have to see in much more detail how these things are internally structured. In this kinetic energy expression, we are using inertia tensor. Now, the issue with this inertia tensor is that first of all, it is a 3x3 matrix, but more importantly, it is being defined with respect to inertial frame or fixed frame. Now that creates a problem. Problem in a sense that in that particular case, inertia tensor is going to change when body is moving in 3D space. So I'll raise this concern over here, that is there any way we can handle without needing to redefine or update the inertia tensor when the body is moving? And yes, we can do that. Actually, this inertia tensor is equal to, if you consider the rotation of the frame the body attached frame alongside it using the similarity transformation. This would be R, which is the rotation matrix, times the inertia matrix defined with respect to body attached frame, which is going to remain fixed, times R transposed. Now in this case, I must write this one down, that this is the inertia matrix with respect to body attached frame. And this is going to remain fixed. We need to define it once, and that would be it. All we then need to do is to account for the rotation matrix that we are going to get from the homogeneous transformations that we have already covered. So in this particular scenario, we can use the inertia tensor in the expression for kinetic energy. Here in the inertia matrix, you are going to find that you have a 3x3 matrix. Where on the diagonal you're going to have the principal moment of inertias, Ixx, Iyy, Izz. And then you're going to have on the upper right triangle at this particular place Ixy, over here Ixz, over here you're going to have Iyz, and similarly for the lower left triangle you're going to have Iyx, Izx, and Izy over here. So these on the upper and lower triangles, these are going to be your product moment of inertias. Let me write that one down. And on the diagonal, let me use a different color. You have principal moment of inertias. Now these are going to depend on the geometry of the object under consideration. So if you're using or computing these for robotic manipulators, probably these are going to be more related to the shape or geometry of the links attached, and you can use either solid modeling exercises or softwares or some experiments to find out these moment of inertias. But generally, in terms of their mathematical formulation, the principal moment of inertias, for example, Ixx is actually a triple integral, where the limits of these integrals are dependent on the geometry of the workpiece of the object, and you're going to find over here the other two variables like y squared plus z squared as a function, and then you need to use the density of the material, which is obviously going to be dependent on x, y, z, and then you have dx, dy, and dz. Similarly, Iyy is going to be also a triple integral, but then you have to use the others like x squared plus z squared as the function, and then similarly the density of the material is being used. And similarly for Izz. Whereas in the product moment of inertias, you're going to have, let's say for Ixy, for example, that is going to be minus this triple integral of x and y, and then you have the density of the material being used, then dx, dy, and dz. But that would be equal to Iyx. So in that sense, you have the inertia matrix to be symmetric matrix. And similarly for let's say xz, you're going to have a similar formulation where you have x and Z multiplied, and then you have the density of the material. And that would be equal to IZX. And similarly, you're going to find one expression for IYZ as well. So in this particular arrangement, you can see that you can use two kind of moment of inertias, one which is called principal moment of inertias, and the others which are called product moment of inertias. Principal moment of inertias are going to remain present always, but product moment of inertias may equal to be zero when you have regularly shaped bodies. And you can use the solid modeling softwares, or experimentally you can verify or find out those moment of inertias. So these are going to be a fixed these are going to be the components of a fixed inertia matrix, which is when used in conjunction with how the body attached frame is rotating in this similarity transformation, you can find out the inertia tensor with respect to the inertial frame. And now I can write down the kinetic energy expression for an N-link robot. But I'm going to start from a single body. And this expression was already written down. I'm going to start from here. The kinetic energy expression is going to have two components, one corresponding to the linear velocity, v, and the other which corresponds to the angular velocity. Now, if I need to jump from this single body to n bodies, or for n-link robot, I have to make a little bit of modification in the expression. So this is going to be the kinetic energy expression which accounts for all these n bodies in it. So that's why it is going to be half summation, where I goes all the way to n because of n body system. And then you have the n masses in there, individual velocity vectors, linear velocity vectors multiplied to give you squaring of it. And then you have the other rotational part similarly constructed. You have a summation over here as well, starting from 1 all the way to n, and then you have the individual angular velocity vectors being used in the expression. Now at this particular stage, I should ask you to consider this linear velocity vector was, when we were deriving these Jacobians, we said that this is going to be equal to the linear velocity part of the Jacobian. And to be consistent with the expression, I'm going to place a subscript I over here, times the joint velocities. And similarly for omega, you identified that this was equal to angular velocity Jacobian part times the joint velocities. So if I can plug in these expression instead of the velocities, I can make use of the joint velocities, which is going to become easy for me because I'm going to have on the joints encoders placed, and I can find the velocities from there. Rotational and translational, obviously, we can have those from there. So by plugging in those expression in there, I can rewrite the expression for kinetic energy, which is going to be now half, and then you have q dot transposed as the first term. Then you can take the summation, and then the Jacobian parts are going to be there, transposed times jvi, and then you have q dot coming in this first expression as well. And similarly, you can write down the other rotational part, q dot transpose, then you have summation again, I is equal to 1 to n, and then you have rather than omega, I have to place the j omega. And then the inertia tensor. All right, now in this particular case, you can also register that this inertia tensor is, we have already defined that this is going to be equal to when you use the rotation matrix, and in this case you have with the same subscript I over there, and then you can use the inertia matrix I, which is fixed. You can compute it once and use it again and again, and then you have rotation inverse or rotation transpose because it is the special orthogonal matrix. So now if you plug in these values, and if you can also see that in this expression you can take these as common from both the expressions, I can simply write down the kinetic energy expression again, and this is going to be equal to half q dot transpose, and you must realize that this is also going to be a vector of all the joint velocities. Then this summation I is equal to 1 to n, and then you can have all the terms in there. And I can plug in this expression in there as well. So there's going to be Ri inertia matrix times the transpose of Ri, and then you have j omega I placed over there, and then you can place the q dots. Now in this particular case, this whole expression which is inside the parenthesis is going to give you one matrix which we call D matrix or inertia matrix. So this whole thing is going to be equal to the D matrix, which obviously is going to be dependent on the configuration of the robot, and this is called inertia matrix. And this is very important matrix because this is going to be very integral part of the dynamic equation or equation of motion for the N-link robot. And the property of this inertia matrix is that it is going to be positive definite. A positive definite matrix is something which is when you have some sort of non-zero vector multiplied after taking the transpose of it on one side and the vector itself on the other side of the matrix. But in that particular sense, if the result comes out to be positive, then obviously the matrix itself is going to remain positive. So this inertia matrix is positive definite matrix, and also it is going to be symmetric as well. So that's also one of the properties of the inertia matrix. And once you're going to derive those, you can counter check that whether your inertia matrix turns out to be symmetric or not. So that would be kind of a counter check whether you have done things correctly or not. So once you're going to incorporate the inertia matrix, you can simply write down this whole expression of kinetic energy to be equal to half q dot transposed times the inertia matrix D, which obviously is dependent on configuration, times q dots. So this is going to be your general expression for kinetic energy of an N-link robot. The potential energy expression, on the other hand, is quite simple for an N-link robot. You can see the first expression over here, which is for single body, which you can use to find out an expression for multi-bodies. So that is over here, just like the summation of all these individual expressions together. So you can write down that for N-link robot. So this expression is what you're going to use in conjunction with the kinetic energy expression that we have derived earlier for N-link robot to formulate the Lagrangian. And that is going to be the necessary ingredient before we start writing the equation of motion for N-link robot. I think this is sufficient for today. We have derived these kinetic and potential energy expressions for N-link robots. We started with a couple of examples, obviously, but we are going to use these concepts in the next part to formulate the equations of motion. But until then, bye-bye.